Hello, everyone. My name is Trevor, and this is my partner, Ryan Lohr.
Our senior project was on a Triboelectric nighttime running vest. Our project advisor is Dr. Rashidi, and this is our senior project presentation. Have you ever been driving at night and passed someone running or walking on the side of the road? Did you have trouble seeing them? Perhaps you are a runner who has ran at night using a lighted vest or a headlamp to make yourself visible. Perhaps you found out halfway through your run that you forgot to charge the batteries as the light dies. Maybe you have forgotten to charge your other battery-powered running devices, or had other battery-powered devices shut down while using them. What if there was a way to capture the energy used while running to power these devices? Well, our device does just that. Here is our outline of our presentation. As you can see, we will cover many aspects of our project, such as background, design, overall results, and future work of our project.
So what is our solution? Well, we want to utilize the runner's motion to create power, and then use this power for lights that will blink to enhance the visibility of the runner in the dark. Now, we also want to utilize low-cost materials, and then recent advances in technology, specifically triboelectrics, to do all of this.
Our initial objective of this project was to create a generator that produces electricity using the movement of a runner instead of an external power source. Secondly, we want to ensure the generator does not hinder the runner's form by causing them to slouch their back or move their arms or legs differently. Lastly, we want to make a device so it can be seen from a distance of 50 feet away at night. We have several contributions to the field of triboelectrics. Our generator utilizes running motion to produce energy. Next, the basis of our design uses a new rectangular prism shape for our generator. We are integrating a triboelectric generator into a running vest, which is novel. Also, we are only using low-cost materials for our device. For some background information, here's a list of energy harvesting types of generators that are alternatives to batteries. The electromagnetic power source uses magnets to produce current. Our triboelectric generator uses charged materials to induce a current. And piezoelectric generators use materials that produce energy as they deform due to a force on the material. We selected triboelectric because of its flexible design. Its designs can bend and be designed for any situation. Triboelectrics have high power output at low frequency as seen in the graph below. The triboelectric generators have a linear output between frequency and power compared to electromagnetic, which has a parabolic tendency. Materials can be designed to be very light in triboelectrics because there are no heavy batteries or magnets incorporated.
So a little background on triboelectrics. There are four basic types of triboelectric generators. The first is a vertical contact mode, where you have two oppositely charged materials that come in contact with each other and separate to induce current. The second is a lateral sliding mode, where these two oppositely charged materials slide back and forth across each other to induce current. The third is a single electrode mode, where you have a single material that is charged. It goes in contact with an electrode and then moves away to induce current. And then final is a freestanding mode, where you have a charged material going back and forth between two similarly charged materials to induce current. Now, these materials are very important. You have a positive material that likes to lose electrons, and the more positive it is, the better it is for a triboelectric generator. And then you have a negative material that likes to gain electrons, and the more negative it is, the better it works for a triboelectric generator.
We have done much research into other triboelectric projects, and these are a few that we used as inspiration. We are interested by the use of fabrics, such as the project shown in the top left, and films to generate power, as shown in the bottom left and the middle. But the fabrication techniques were not available for us to do similar applications. Our design is similar to the spherical generator shown in the top right, but in rectangular design form using the vertical contact method. Also, the shoe generator in the bottom right uses similar movement to create power, but our design more readily makes power available rather than powering something directly from a shoe.
Our working principle is that of a freestanding vertical contact mode. So essentially, the picture that you see in front of you is each step in a runner stride. So at A, the runner is at rest or beginning to lift off with one foot. So the negative center is against the bottom positive material, and there's no charge moving in the circuit. As the runner lifts off the ground, the negative center moves towards the top, inducing a current to balance the charges. Once the negative center reaches the top, all the charges are balanced, and the negative center stays there until your body lands against the ground and you rapidly decelerate. As you rapidly decelerate, the negative center moves to the bottom again, inducing current within the circuit, and then you move back to position A where everything is at rest. For materials, we chose Captain for the center because it is very good at gaining electrons, and then we chose aluminum for the positive material because it can act as both a triboelectric material and as an electrode. Our basic design has 5 parts to it for our generator. The first is the Captain center, which is rectangular in shape and hollow. The hollow is to allow us to put ball bearings inside of it to increase the density, after which it is covered in Captain tape for the triboelectric material. The gray pieces are the holders. These pieces are covered in aluminum foil, and then the aluminum foil is designed to deform as the Captain center hits it to ensure maximum contact area. These pieces are held all together in the green housing pieces, and the holders actually snap into the green housing plate pieces for easy assembly and disassembly. Each unit is put in a combination with another unit, which we call a generator unit, and then ends are placed on these pieces. These end pieces have cylinders that come out of them with little notches that allow us to use snap connectors to connect one generator unit to the next. There's a total of 12 generator units for 24 total generators. For our LED holder, it is very similar to that of a flashlight. In the section view on the left, the LED goes at the bottom of the cone. The cone itself has a reflective sheet that goes all the way around it, and then there's a lens on top. Around the bottom of the outside, you see little holes that are used to sew the LED holder to the vest itself. For fabrication, all of our parts were 3D printed using ABS. The triboelectric materials were then attached using Scotch tape and super glue, and then everything was snapped together. In the upper left-hand corner, you can see a fabricated LED holder. This includes the 3D printed cone, the lens, the reflective material, and then the LED in the bottom.
The fully assembled vest has 2 pouches on the back to hold 6 units of 2 generators each. The LED cones are sewn onto the back of the top pouch and to the front of the jacket. Each set of 12 generators is also inside a cloth bag inside the pouch to help protect it from the elements. Running with the vest, you will notice a slight weight on your back, which is noticeable but not heavy. This doesn't hinder the runner's form in any way. The generators are also slightly noisy, but hard to hear over the footsteps while running anyways. We were able to produce positive results by powering the red LEDs with the generators. Pictures on the left were done inside with the lights on and off while the operator was running in place. The picture on the right was taken outside at night. The LED could be seen blinking clearly up to 120 feet away from the person wearing the device.
We also tested the generator for optimal results. So on the left, we have a maximum power point graph for different frequencies. It was determined that 3 Hertz or 180 steps per minute is the optimal frequency. Before that, you have a linear increase, and then after that, you have a slow drop off due to bouncing within the generator. On the right, we tested the generator for different stride heights, and it was determined that on the up stride, the voltage increases as step height increases, and then on the down step, the voltage decreases as step height increases. So these results were inconclusive as to whether there is a optimal step height or not. There are a lot of classes that helped us along the way. Specifically, mechanical design principles helped us design out all of our parts and tolerancing for these parts. Manufacturing processes helped us with the 3D printing, and that the ABS actually warps during the 3D printing process, and we had to account for this. Material science and mechanics of materials helped us with the modulus elasticity for all of our snap connections. Statics, dynamics, and physics helped us with analyzing the negative center at every point within the stride. Energy systems helped us with our maximum power point graphs, and control systems helped us with our wiring.
In summary, we have developed a solution to improve the safety of runners at night without batteries. We have designed a triboelectric generator that utilizes the motion of a runner's stride to provide power. Our generators were built using 3D printers, assembled and attached to a vest along with LEDs. We tested our design for optimal conditions and range of visibility. Our optimal conditions were found to be at a running pace of 3 Hertz, and the vest can be seen up to 120 feet away.
For projects that come after us, there are a few ways to improve upon our project. The first is materials. Specifically, triboelectric materials are being found every single day, and ours are not analyzed at the nano level. So between the analysis at the nano level and the various new materials that are coming out, these can be massive improvements upon our design. Additionally, as I stated before, ABS does work during the 3D printing process, so a more accurate construction material could be used. As far as our design goes, you can always make a design more flexible and more lightweight, which will help improve everything overall. And then the greater the surface area of the generators, the more power output they have, so this would also be a way to improve upon our design. Lastly, we want to thank everyone that helped us along the way with our project. We want to thank our professors, Professor Rashidi, Professor Hunt, and Professor Bryant for all the help they provided. We want to thank several students, Samantha Barker, Brady Miller, Brandon Mott, and Kimberly Wick for helping us. And then a special thanks for funding from Lindy, which was formerly Praxair, and the IAB Executive Committee. Thank you for watching.